Okay, let's talk about the size of sets. We've talked about how big real numbers are and how to measure them, find the difference between them and that sort of thing, absolute values and inequalities. But if I have a set, how do I tell how big that set is? Well, we could count the things in it. That'd be fine, right? Like the set A, B, C. If I asked you for the size of this, absolute values again are kind of a measure of how big something is. The size of that is, well, there's 3 elements in there. That's the same as the set, say 100, 999, or 10 to the 10. Right. This, as a set, has 3 numbers in it. It's still size 3. Why do we say those both have the same size? Well, there's a one-to-one function, or a one-to-one correspondence between them. I can map A to 100 and 100 back to A. I can map B to 999 and 999 back to B, and same thing with C and 10 to the 10th. Okay. This is the idea of how we're going to measure sets. So I need to talk about one-to-one functions so we can get those one-to-one correspondences, and then let's try and use this on some things, some sets, and see how big they are. So, one-to-one functions. If you remember back from teaching algebra or from taking your algebra course, a one-to-one function is a function that if 2 outputs are the same, they had to have come from the same input, right? So different outputs come from different inputs. Different inputs give you different outputs. That's sort of how we state these things in real language. Mathematically, f is a one-to-one function if f of x equal to f of y, then x equals y. So if the outputs were the same, we must have had the same input. Right. This is an if statement that goes one direction. We'd been working with if statements that had both directions before. The other direction is just the definition of the function. A function exists if you take the same input, you put it into the function, you better get the same thing out, right? So the other direction of this if statement is just the definition of being a function. This actually has some merit to it, some meat to it. There's more than just, oh, it's a function. No, the converse, 2 outputs being the same, then the inputs are the same. So let's do an example. F of x equals x cubed is 1-to-1. A term that probably the book will use, injective. So a one-to-one function is also known as injective functions. It's just a fancier term for one-to-one. Something real math books use instead of writing out 1-2-1. We get to use the word injective. So the proof: if say x cubed equals y cubed, then we want to show that x is equal to y. So what we have to do is we have to solve this equation, right? X cubed minus y cubed equals 0. And I can factor that, x minus y times x squared plus xy plus y squared, right, equals 0. So x minus y equals 0, or x squared plus y squared plus xy equals 0. And this is what we want, so I'd have to show that this is never equal to 0, right? So how might I show that that's never equal to 0? Well, we can solve it as a quadratic in x. So x equals negative y plus or minus the square root of y squared minus 4 times 1 times y squared over 2. So x equals minus y plus or minus the square root of negative 3y squared over 2. This is imaginary. So it's never equal to 0. So the only way that this could be 0 is if x minus y equals 0, giving us x equals y. Alright, so we have a proof that the cubing function is injective. We could have seen this more easily just by looking at the graph of it, but the functions we're going to work with, we can't necessarily graph them, right? The graph of this function is injective because it passes the horizontal line test. Any horizontal line you draw through this graph only crosses the graph exactly once. Why does that make it 1-to-1? Well, had it crossed the graph, say twice, say this output here, this y value here, would have corresponded to an x comma y and an x 2 comma y. So let's call this x1. Two different input values would have given me the same output value. That's in direct conflict with the statement that any two outputs that are the same came from the same input. So horizontal lines correspond to an output. If there's only one specific output that you can get from the function, or one input that gives you that output, you have a 1-to-1 function. Okay. Some more examples. Let's show that the natural numbers and 2 times the natural numbers are the same size. Okay, so I have an infinite set, I've got another infinite set. Well, they're both infinite, so we kind of think that they're the same. But we have different sizes of infinity, as we'll see later. These two infinities are the same. Okay, so I need a correspondence. Let's take f. It's going to map the natural numbers to 2 times the natural numbers, which takes x and changes it to 2 times x. And I need a 1-to-1 correspondence the other way. So this says that n fits inside 2n. We need 2n to fit inside n. And what we're going to do is we're going to take some number, let's say y, and we're going to, since it's an even number, we're going to divide it by 2. Okay. This is going to get us this correspondence that we need. These are 1-to-1. So f is 1-to-1 since if we have f of a equals f of b, then f, then 2a equals 2b, divide by 2 on both sides, a equals b. And sort of very similarly, g is injective. I'll use that word this time, since if g of a equals g of b, a over 2 equals b over 2, which means that a equals b by multiplying by 2 on each side. Okay. So I have an injective function from one into the other. That means they kind of fit inside of each other, right? And they fit inside without any overlaps. 1 to 1 means there's no overlaps. Alright, so this is going to be our definition of when two sets have the same size. A and B are the same size, have the same cardinality, if there exists two injective functions f mapping A into B. That hook arrow means into, and G mapping B into A. Okay. So f takes a function from A to B, f is a function from A to B, and G is a function from B to A, and they are both injective. Kind of says A fits inside of B using the function f, B fits inside of A using the function G. We saw earlier this worked for my ABC 1, 2, 3 type things. So it works for finite sets. It works for countable sets. We just saw that the integers and twice the integers are the same size because there's 1-to-1 correspondence between them. Let's see an example where it doesn't work. And we're going to see something kind of famous called Cantor's diagonalization argument. Okay. The size of the real numbers is bigger than the size of the natural numbers. Okay. So there are more real numbers than natural numbers. This leads to two different sizes of infinity. So I've got an uncountable set and a countable set. It's an infinity, but it's sort of countable, right? I can list off, here's the first one, here's the second one, the third one, the fourth one, and so on, right? I can go through 1, 2, 3, 4, and I can count them. The real numbers we can't count. There's too many of them. There's more than the countable number. I can't say this is the first one, and then this is the second one, and then this is the third one. Because if I could do that, then I could find an injective function from the reals to the naturals, right? We just said, here's the first one. That goes to 1. The second one goes to 2, and so on. But we can't do that. Let's see that we can't do that. The argument goes, there is no injective function from R to N. Okay. So suppose, for example, there was. Say f maps the real numbers into the natural numbers. I just need it to be injective, so I don't know that necessarily 1 has an input associated to it, right? I might not have f of anything equals 1. Maybe the first number that I get to is 10 trillion. But I can still, since I can order the natural numbers, I take, okay, what was the first output that we actually got hit? We'll say that that came from x1. Say f of x1 is less than f of x2 is less than f of x3. Since the natural numbers are ordered, we can order the inputs that way as well, right? Okay, now that I have that order established, let's write out these numbers in that order. Say the lowest input from f comes from x1, which I don't really care about what happens before the decimal, but after the decimal, I'm going to say this is D11, the first digit of the first number. The second decimal digit of the first number is going to be D12. Third digit is going to be D13. D14 is the fourth digit, okay, and so on. I don't care what happens before the decimal. So say x2 equals this. This is D21, D22, D23, D24. I don't care what happens with x3 before the decimal. After the decimal, I get D31, D32, D33, D34, and so on. And I can do this with all of the numbers in the list. Okay, and these go on because these are real numbers. They have infinite decimal places, or maybe they don't, but if they don't, then I just put zeros out here at the end. And it goes on this way too. Alright. We need to find a number that doesn't match any of the numbers in the list, and then I can show that there's not an injective function. So what I'm going to do is I'm going to look at this diagonal. I'm going to look at D11, D22, D33, D44. And if I change this guy, if I change him, and I change this guy, and I change this guy, and I change this guy, I don't care what happens before, so I'm just going to say let's x equal 0 point. I'm going to take maybe D11 and I'm going to add 1 to it. And then D21 and add 1 to it. And D31 or D22, D33 and add 1 to it, and so on. So now I've changed all of these decimals. The only problem is maybe if I had a 9 in one of the digits, then what should I write down here? Well, 9 plus 1 is 10. That's not a digit anymore. I'll just use it as 0, right? So if dxx equals 9, say dxx changes to 0. Alright. Now, this number that I've written down doesn't happen, it doesn't occur in the list. Right? Because the first digit's different than this number, right? It's different than x1. X isn't equal to x1 since D11, the first digits are different. X isn't equal to x2 since the second digits are different, right? X doesn't equal xi since the ith digits are different. Okay, So it's never in that list. That means that I didn't have an actual injective function. It didn't take all of the real numbers and send them to natural numbers. I missed one. I missed x. Okay. So there can't be an injective function. This is absurd. This is a contradiction to f mapping r into natural numbers. We don't have an output. We don't know what f of x is. Okay. So that means, this means there is no injective function from R into N. R is uncountable. So, different sizes of infinity exist. In fact, there's bigger than uncountable infinities. If you take the set of all sets of real numbers, that's bigger than the uncountable infinity. There's an infinite number of infinities, each one larger than the last one. In fact, the continuum hypothesis talks about that. So, are there a countable number of infinities, or are there an uncountable number of infinities? Nobody knows. Right now, we can construct a countable number of infinities, but maybe there's some infinities between those infinities that we don't know about. And we'd have to show that there's a whole lot of infinities between them. That's kind of a big unsolved math question. Alright, until next time.